Okay, I want you to imagine, just for a second, trying to find a single, completely microscopic broken switch. Now imagine that switch is buried inside a literal silicone maze right alongside billions of other identical switches, and all of them are completely invisible to the naked eye. Oh, and by the way, you have to do this flawlessly, for millions of devices without accidentally destroying any of them. Sounds like a totally daunting, frankly impossible task, right? But in the world of modern semiconductor engineering, solving this billion transistor problem isn't just some fun theoretical puzzle. It is a daily, absolutely non-negotiable requirement. And what happens if you fail to find that single broken transistor? Well, you're going to run headfirst into a terrifying financial reality that the industry calls the rule of 10. Basically, the cost of detecting a fault multiplies by an order of magnitude at each subsequent stage of the product lifecycle. So if you find a bug during the design phase, no big deal, it's a relatively cheap fix. But if you miss it and catch it later during manufacturing, boom, it costs 10 times more. And if that defective chip actually makes it out into a customer's hands or into a deployed system, there is literally no way around it. You are paying 100, maybe even 1,000 times more to clean up the resulting disaster. You either find the problem early or you pay for it dearly. So let's dive right into this explainer and meet the actual hero of our microscopic detective story. Today, we are unpacking design for testability, or as it's commonly known, DFT. We're going to explore exactly what it is, why it's an absolute cornerstone of modern hardware architecture, and how it practically guarantees that those microscopic switches work exactly the way they're supposed to. Here is our roadmap for today. We'll cover 1. The billion transistor problem. 2. What is design for testability? 3. The test engineer's toolkit. 4. Maximizing yield and success. And 5. The future of testing. All right, let's kick things off with Section 1, the billion transistor problem. So because wafer yield is invariably less than 100%, defects introduced during manufacturing are just unavoidable. It's a fact of life. That means every single fabricated chip has to undergo rigorous screening before it ever reaches a customer. Now, the old way of doing things treated this testing as a downstream activity. Basically, build the chip first and then figure out how to validate it post-fabrication. But when you're dealing with billions of transistors, that method quickly creates massive validation bottlenecks and requires impossibly complex, super expensive redesigns if something goes wrong. The new way, the gold standard for modern high-complexity designs, is what we call a shift-left approach. Test structures are integrated right into the earliest register transfer level, or RTL, development stages. By shifting the testing to the left side of the timeline, you solve problems before they are literally baked into the silicon. Moving on to Section 2. What is design for testability? The really crucial point here is that DFT is an engineering methodology that purposefully embeds specialized test features directly into the hardware from day one. Think back to that integrated circuit as a vast, highly complex microscopic maze. If you're standing on the outside, how do you possibly know what's happening deep in the center? Well, you need two things. First, observability. These are your windows into the maze. It's the ease with which internal logical states can actually be read from the external output pins. Second, controllability. These are your levers. It's how easily you can force specific internal logic nodes into a known state, like a 0 or a 1. DFT is entirely about building those exact windows and levers directly into the maze itself. Which brings us to Section 3, the test engineer's toolkit. So how exactly do engineers build those windows and levers in real life? The first major tool they use is the scan chain. See, in highly integrated circuits, you simply can't access internal logic directly through the external input and output pins. Scan-based testing solves this problem by taking internal flip-flops and connecting them together to act like shift registers whenever the chip is put into test mode. This effectively turns deeply buried, totally hidden internal nodes into a chain of readable, controllable data, all without needing any invasive physical probing. Next up, we have BIST, or built-in self-test. You can think of this as giving the chip its very own internal doctor. BIST enables autonomous, at-speed testing directly within the logic and memory blocks of the chip itself. This is huge because it dramatically reduces the reliance on incredibly expensive external automatic test equipment, or ATE. The chip essentially generates its own test patterns and checks its own responses. This is absolutely critical for automotive and aerospace applications that demand constant on-the-fly diagnostics while they're actually out in the field. And guiding all of this is ATPG, Automatic Test Pattern Generation. ATPG acts as the software brain of the entire operation. These advanced tools automatically generate the exact test vectors, meaning the specific sequences of ones and zeros needed to activate and hunt down very specific microscopic defects. We're talking about finding a single transistor permanently stuck at zero, or a signal that's failing to transition fast enough. ATPG ensures the testing is mathematically optimized to find the absolute maximum number of faults in the absolute minimum amount of time. Let's move right along to Section 4, Maximizing Yield and Success. At the end of the day, DFT isn't just about doing cool engineering, it's about economics. The ultimate scorecard for semiconductor manufacturing is yield. Yield simply equals the number of passing, defect-free devices divided by the total number of manufactured devices. That's it. The entire goal of DFT is to push that number of passing devices as close to the total as mathematically possible. It's all about ensuring that you are consistently shipping reliable, known good die, and definitely not throwing away millions of dollars in defective silicon. So how exactly does DFT drive that high yield and guarantee first-pass design success? Well, first, by providing direct access to internal states, it reduces hardware debug cycles from grueling multi-week guessing games down to highly controlled analyses that take just days, a real game changer. Second, it enables realistic system-level testing, so you can actually verify that components behave correctly under real-world workloads. Third, it allows for early defect containment and adaptive binning. This means you patch the bad chips early and you properly categorize the good ones based on their actual performance limits. And finally, advanced DFT allows engineers to collect data on how the circuit performs under real-world process, voltage, and temperature variations. That ensures the chip won't just fail on you the second things get too hot or the voltage fluctuates. And finally, Section 5, the future of testing. As semiconductor processes shrink ever further down into the deep submicron regimes, and as we start doing things like stacking multiple dies in 3D packages, the sheer density of the logic is forcing testing protocols to evolve at breakneck speed. Today, much of our testing relies on model-based fault coverage, but tomorrow's testing, it's all about AI-driven adaptive test optimization. Test programs are increasingly deploying unsupervised machine learning algorithms directly onto massive volumes of scan failure data. By using advanced techniques like root cause deconvolution, AI can analyze test responses in real time, dynamically adjust test sequences, skip redundant vectors, and systematically isolate fabrication failures so much faster than humanly possible. But looking ahead to future challenges, there is one tension that really stands out above the rest: the rising conflict between testability and cybersecurity. Remember those windows and levers we talked about building into the chip? Well, if a test engineer can use them to control internal states, a malicious hacker could potentially use them too, maybe to extract secret keys or tamper with the device. So the future desperately requires secure by design testing. Engineers have to implement scan chain obfuscation, encrypted test data, and highly secure access protocols. They have to make sure that the very features designed to guarantee the chip works don't become the exact vulnerabilities that compromise it. I want to bring this all back to a really profound industry warning from Averna. Testability is easy to postpone, but very expensive to fix later. That hits the nail on the head. DFT is absolutely not an optional add-on. It's a non-negotiable strategic asset. Embedding testability frameworks into the architecture from day one is literally the only way to transition from reactive troubleshooting to predictive, profitable quality assurance. Which leaves us with a pretty fascinating question to ponder. As these chips become almost unfathomably complex, holding billions of transistors right in the palm of your hand, how will AI and machine learning reshape the future of not just secure, but potentially self-healing chip design? We are rapidly entering an era where our devices might not just test themselves, but dynamically repair themselves on the fly. And to think, it all starts with the ingenious microscopic detective work of design for testability. Thanks for joining me on this explainer, and keep questioning the incredible hidden engineering inside your everyday devices.